The paper is Reinforcement Learning via Self-Distillation by Jonas Hubater and colleagues from ETH Zurich, MPI, MIT, and Stanford. Paper ID is 2601.20802V1. Here is the core problem. Current RL for large language models, specifically RLVR, it relies on these scalar rewards, basically just a simple pass or fail signal. And this creates a huge credit assignment bottleneck. The model, well, has no idea which specific token actually caused the failure.
Exactly. And the solution they propose is SDPO, or Self-Distillation Policy Optimization. It uses what they call rich feedback, so things like compiler error messages or the outputs from unit tests. It treats the current model as a self-teacher. So when an attempt fails, the model looks at the question, its own wrong answer, and that error message to retrospectively figure out what the token probabilities should have been. Then it distills those corrections back into itself.
And the results are pretty stunning. SDPO outperforms GRPO on major benchmarks like LiveCode Bench v6, and it gets to the final accuracy with 4 times fewer generations. Plus, it produces reasoning chains that are up to 7 times more concise. And, maybe most importantly, it enables a 3 times faster discovery of solutions for really hard problems at test time, way better than best-of-case sampling.
That's the 1-minute version. Now, let's actually dig in, because this paper, I think, really lays out a different path for post-training than what most of us are used to.
Right. So to set the stage for everyone listening, if you're working in post-training, you're probably living in the world of RLVR, that's reinforcement learning, with verifiable rewards. It's the standard way of doing things.
Yeah, you take a model, give it a problem, it generates a solution, you check if it's right.
And that check is usually binary, right?
Yeah.
Did the code pass, yes or no? Did the math answer match? +1 or 0.
And that's the thing, it works. I mean, it's how we got a lot of the great reasoning models we have today. But this paper argues it is just incredibly inefficient. They call it the scalar bottleneck.
It's a great term for it. Because think about it from the gradient's point of view. You've got a sequence of, what, maybe 2,000 tokens?
Could be, yeah.
And you get a single reward back. 0. The algorithm now has to guess, purely through trial and error, over thousands of attempts, which one of those tokens was the bad one.
Was it a logic flaw in the first paragraph? A syntax error on the very last line? The scalar reward just hides all that useful signal.
It's like your professor handing back a term paper with just a big F on it. No notes, no red ink. You have to rewrite the whole thing blindly, hoping you fix the problem without, breaking the parts that were actually good.
Precisely. That's the sparse reward problem in a nutshell. And it leads to terrible sample inefficiency. You just have to burn so much compute to learn anything.
So this is where the paper introduces RLRF reinforcement learning with rich feedback. The idea is that the environment usually isn't silent. In coding, it's practically screaming at you.
It really is. If your Python script fails, you don't just get false, you get a full traceback. You get an index error, list index out of range on a specific line.
All that rich, dense information. And the core idea of SDPO is, why are we throwing that away? Why compress it all down to a single bit of information?
Exactly. If we can just feed that rich feedback back into the model, we can turn this sparse RL problem into a much, much denser supervised learning problem.
Okay, let's talk about the mechanism. This is where the self-distillation part of the title really comes into play. Because when I hear distillation, I usually think of GPT-4 teaching a smaller model. But that's not what's happening here.
No, and that's a really critical distinction to make. This is on policy distillation. The model is its own teacher. And it works because of a really interesting property of LLMs.
Which is?
They're much better at correcting a mistake in hindsight than they are at generating the perfect answer from scratch.
That feels intuitively true. I can find a bug in my own code way faster than I can write that same code perfectly the first time.
Exactly. So here's how the SDPO algorithm works. Step 1. The student, that's your current model, tries to answer a question, $6, and it generates an answer, Yarzel.
Okay. And it fails.
Right. It fails, but the environment gives back that rich feedback, $5.
So now we have a set of 3 things. The question, the wrong answer, and the feedback.
Step 3 is the magic. It's the self-teacher step. You take the exact same model, maybe a frozen copy, but the same weights, and you prompt it with all 3 of those things. You basically ask it, hey, given that you generated this wrong answer, and here's the error it produced, what should the right tokens have been?
So it's performing a retrospective. It's looking back on its mistake.
Yes. And conditioned on seeing that error message, the model calculates a new set of log probabilities for the sequence. It's saying, oh, I see that index error now. I realize the probability of token should have been much lower and N1 should have been higher.
And then the final step is just distilling that new probability distribution back into the original student model.
Correct. You use KL divergence to nudge the student's policy to be more like the teacher's corrected policy.
And this just completely solves that credit assignment problem we started with, because now you have a target for every single token in the sequence.
It's dense supervision. The loss isn't smeared across the whole sequence. The teacher might say, look, the first 50 tokens were perfect, don't change them. But token 51, that's where you went wrong. You get a gradient signal right where it's needed.
Which explains the speed.
It explains the massive speed up, yeah.
So let's get into the performance. The paper compares it directly to GRPO. And for anyone listening, GRPO is important because it's kind of the current state-of-the-art for reasoning. It's behind models like DeepSeek R10.
It is. GRPO is a solid baseline. It groups multiple rollouts together to try and normalize the rewards and reduce variance, but it's still fundamentally based on that scalar reward.
So head-to-head on LiveCodeBench v6, what did the numbers look like?
SDPO hits a 48.8% pass rate, while GRPO gets 41.2%. That's a pretty substantial leap on a tough coding benchmark. But the number that really jumped out at me, and I think matters for anyone paying for compute, is the sample efficiency.
Right.
SDPO reaches GRPO's peak accuracy using only a quarter of the generations.
A quarter. So you're basically training 4 times faster.
Roughly, yeah. Because with SDPO, every single failure is a valuable learning opportunity. With GRPO, a failure is often just wasted compute unless you get lucky and another attempt in the group happens to succeed.
There was another result that I found fascinating, and that was about verbosity. We've all seen this trend where RL-trained models start to ramble.
Oh, yeah, the long chains of thought. Let me think about this. Wait, let me double check my work.
Exactly. It's a form of reward hacking, right? The model just learns that generating more tokens often correlates with eventually stumbling upon the right answer.
It's like a student padding their essay to hit the word count. It's not deeper reasoning, it's just more output.
But SDPO didn't do this.
No, it did the opposite. The answers it generated were significantly shorter while also being more accurate. The paper has this great example in Figure 7 with a chemistry problem.
I saw that one. The GRPO model just gets stuck in a loop. It's repeating calculations, saying, and wait, and takes over 5,000 tokens.
Right, 5,500 tokens. And the SDPO model gets the same problem. Lays out the steps logically, does the math, and gets the answer in 764 tokens.
That is a 7 times reduction.
It's huge, and the authors argue it goes right back to that rich feedback. If you learn from a specific error message, you learn precisely where your logic broke. You don't learn the meta strategy of just talk more, you learn fix line 4. The supervision is precise, so the policy becomes precise. It cuts out all the filler.
And that's a massive win for inference costs in production. Better accuracy with 7 times fewer tokens. That's a no-brainer.
Absolutely.
Okay, I want to push on a potential limitation here. This all sounds great, but it seems to depend entirely on having this rich feedback. Code gives you tracebacks. What about other domains, like science Q&A? If the right answer is C and the model says B, there's no error message.
That's a very fair point, and they actually have a clever workaround for that. They call it group-level feedback. So, in those sparse reward environments, SDPO will look at an entire batch of attempts.
So it'll generate, say, 16 different answers to the same question.
Right. And let's say 15 of them fail, but one of them succeeds. SDPO then takes that one successful attempt and treats it as the feedback for all the other failed attempts.
I see. So the self-teacher's job becomes comparing the failed answer to the successful one and saying, look, this is what you should have done.
Exactly. It's still a form of self-distillation. It's just distilling from a successful peer in the group instead of from an error message. It lets the method work even without rich feedback, though the gains are definitely highest when you have it.
And does this scale? I mean, a lot of these self-correction ideas fall apart if the base model just isn't smart enough to teach itself.
And that is absolutely true here as well. They ran tests on a small 1.5 billion parameter model, Quen 2.5, and the gains were pretty negligible.
Because if the model isn't smart enough to understand the error message,
then the teacher is just as confused as the student. You're just distilling noise back into the model, verifying garbage with garbage, essentially.
So you need a certain level of base intelligence for this to work.
You do. They found the technique really starts to pay off around the 8 billion parameter size. You need a model that has enough reasoning ability to actually look at an error and understand its root cause.
Okay, one last training detail before we get to the really wild inference time stuff. Catastrophic forgetting. It's the classic RLVR nightmare. You train a model to be great at coding, and suddenly it can't answer basic questions anymore.
And this is where being on policy is a huge win for SDPO. Because the model is always updating based on its own distribution, it's not being yanked towards a totally different model like GPT-4. It stays within its own manifold of capabilities.
So it doesn't kind of lobotomize itself for the new task.
Right. They tested it on holdout task and found it maintained its general abilities much better than off-policy methods. It sharpens a specific skill without overwriting its general knowledge.
All right, let's get to what I think was the coolest part of the paper, test time discovery. This is where they go beyond just training and start to reimagine what inference can be.
This section tackles the problem of what they call impossible tasks. They set up problems where the base model had a pass at 64 of less than Bray 3.
Which basically means it has a 0% chance of solving them.
Pretty much. And in a normal RLVR setup, you're stuck. You can't learn without a positive reward. If you never solve the problem, you never get a reward, you never get a gradient update, you are just dead in the water.
So how does SDPO solve a problem it literally can't solve?
By learning during the test, this is the wild part. The model tries to solve the problem at inference time. It fails. It gets an error message. Now, normally you just feed that error back into the context window and say, try again.
Right, like multi-turn prompting or a reflection-style agent.
But context windows fill up. SDPO does something completely different. It takes the error, calculates the gradient, just like in training, and performs a weight update on the model right then and there.
It actually fine-tunes itself temporarily during inference.
Yes, it runs a little mini optimization loop on its own weights. It's effectively compressing the lesson from that failure directly into its own brain.
So the context isn't just in the prompt anymore, it's baked into the weights.
They call it compressing context into weights, and the results are just incredible. They compared this to best-of-case sampling and multi-turn prompting on one particularly nasty problem.
Question 3, I think it was.
That's the one. It was a beast. They let the standard methods run for 2,750 attempts.
And the result?
0 solutions. Not a single success in 2,750 tries.
In SDPO, with this test time learning.
It found a solution after 321 attempts.
Wow. That feels like it shouldn't be possible. It just pulled a solution out of nowhere by iterating on its own failures and changing its own mind.
It's not magic, it's just gradient descent. But applied in a new context, it suggests that inference doesn't have to be this static one-shot process. We can treat hard problems like mini training runs.
Okay, I can almost hear the ML engineers listening getting nervous. Updating weights at inference time sounds computationally heavy. Is this actually practical to implement?
Surprisingly, they claim it's not that bad. If you already have a PPO or GRPO pipeline, SDPO is designed to be a drop-in replacement. You're mostly just swapping out how the advantage is calculated.
So instead of advantage being the reward, it's the distillation loss.
Exactly. Now, there is more compute overhead per step. You have to do that second forward pass for the teacher to get corrected probabilities.
But it's parallelizable, I assume.
It is. And when you factor in that you need 4 times fewer steps to converge, the total wall clock time could actually end up being lower.
They also mentioned a couple of tricks for stability, which makes sense. If a model is teaching itself, you'd want some guardrails to stop it from spiraling.
For sure. They use an EMAA, an exponential moving average, for the teacher's weights. So the teacher is always a slightly smoothed, more stable version of the student's recent history. It stops it from oscillating wildly.
And something about memory.
Top K distillation. Yeah, calculating KL divergence across 100,000 token vocabulary is huge for VRAM. So they only compute the loss on the top 100 or so logits.
Because the probability of the other 99,900 tokens is basically 0 anyway.
Right. It captures almost all of the important signal, but for a fraction of the memory cost, which makes it much more practical.
All right, we're coming up on time. Let's just zoom out. This paper, to me, feels like a real pivot. We've spent so much time building complex external reward models. SDPO just says you don't need that. You just need a compiler and a mirror.
That's the big shift, I think. Moving from reward-based learning to feedback-based self-supervision, we're finally starting to use the rich signal that the environment gives us for free.
It's a clear step towards more autonomous systems. The model in the paper literally outperforms its own teacher, which was itself from an earlier step. That's the positive feedback loop everyone in this field is trying to build.
It is. Once you remove the bottleneck of human-labeled data and you remove the bottleneck of needing a smarter teacher model, the only things left are compute and the quality of the feedback from your environment.
So it's the final thought for everyone listening is this. This paper shows a model can self-improve using just compiler errors, with no human data in the loop. If we can build environments that provide rich feedback, not just for code, but for math, physics, logic, are we looking at the blueprint for a kind of open-ended, autonomous self-improvement?
If a model can reliably verify its own mistakes, it can fix them. And if it can fix them, it gets smarter. If it gets smarter, it can tackle harder problems and fix harder mistakes. That's the flywheel.
A fascinating possibility. That covers reinforcement learning via self-distillation. The paper ID, again, is 2601.20802E1. Thanks for tuning into AI Paper Podcast. We'll see you in the next one.